let's classify the coatings by the yeah. Oh, we have a chat. Hi, Nikita. Sure, I will let you in. Hi again. I'm glad that you have joined in. So
yes, hello.
Some people are gathered, and we will. We have just started.
Thank you. Good day to all. Great to hear you. Great to see you. Thanks for coming. Let's move on.
Yeah, let's move on. So I think I have to restart now. The coatings. First, what we do is to classify them by the production method. Basically, in architecture, we're using two types of coatings. Architectural one, pyrolytic or CVD, meaning chemical vapor deposition, or hard coating is one type. Magnetron or soft coating is another. To understand why they differ so much between themselves and why do they have properties, certain properties, we need to start from the production method of those coatings. And first, we will be talking about pyrolytic. The process itself is rather simple. The coatings, the material of the coating, usually it's titanium oxide or tin oxide, deposited, doped with some kind of tar or other materials, is sputtered on a float ribbon, which has already been formed. In some cases, the coating device is positioned in the end of the tin bath. In some cases, it's positioned directly after the end of the tin bath, but really it matters not. The thing is that the material is sputtered on a hot glass ribbon on a float line. That is why it is sometimes called on-line coating. And the material is fused with the glass by the very hard bond because of the very high temperature. Yeah, Nikita has left us because he's on the road, so we will move on without him. What do we get as a result? We get a single layer of coating on a glass. And meaning that we cannot produce multiple layers with the technology. So a single layer, very hard layer with a very good bond within the glass. That's what we have. And that determines the properties of the coating. It's very high physical, chemical resistance. And it also determines that we may not vary the coating types. So what do I mean? If, for example, we want to have a different parameters or a different look of the glass. In the case of pyrolytic process, we have to sputter the same coating, but on the glass of a different color. That is why we may have blue, bronze, green glass with one coating. So the color and the characteristics we are getting by changing the underlayer type, the glass type. And that really not allows us a great amount of flexibility in terms of production. What can be done? The coating may be deposited on the glass in a different way called a magnetron process, or depositing in magnetron depositing in vacuum. This is another type of beast. The line itself is completely separated from float line, and the glass which is getting in this machine, in the coater, in the coating machine, is cold and already cut to size. So here we're not depositing on a glass ribbon, we're depositing on a ready-made piece of glass, which we're taking from warehouse or directly from float line. It really doesn't matter. The line itself consists of many chambers positioned right after another and connected by the conveyor on which the glass is moving from one chamber to the other. That is done so we may deposit multi-layered coating, because in each single chamber, we're putting a single material on the glass. Let us see the process, how it is done, and how this pattern in a single chamber is happening. Here is the schematic of a single chamber. So in the bottom, you see the conveyor on which glass is moved and slowly moving. And in the beginning of the process, the air is removed from the coating line. So we have quite deep vacuum inside. After the air has been removed and the process is started, some gas is put in. It may be different type of gas like argon, oxygen, nitrogen, depending on which type of layer we will be putting in. Gas is there in small amount, so the pressure is extremely low, so it's almost a vacuum. But then on the top we have a cathode, so negative, and anode, positive. And we turn the electricity on, and that creates electromagnetic field in the chamber. Also, electromagnetic field ionizes the gas. So instead of having gas, you will start to having plasma in there. Plasma and ionized gas is the same. What is happening? As usual, if you take a molecule of any material, it has a nucleus, a core, with the positrons and neutrons in there. So it has a positive charge. Around there is a cloud of electrons, which are constantly moving in a certain volume. When put in electromagnetic field, the electrons from this molecule may leave the cloud, but electron has a negative charge. So negative charge goes away and leaving you with ion. Ion is the molecule, but without one or more electrons in there. So it is having a positive charge. After ionization, you have free electrons and these ions. So what is happening? Ion has a positive charge, but the cathode on top of the chamber has a negative one. So positive accelerates towards the negative, and the ion obtains speed necessary for strike the target. Target is the block of material positioned before the cathode. So ions are bombarding the target and pulling out, knocking out the molecules of the target, so they may be deposited on the glass below. The target materials can be quite different. For example, in all glass which having a low E properties made with magnetron process, the key material is silver. So here you have a target weighing 20 plus kilos of silver and with the purity of 99.99%, so very pure. You put argon gas there. Argon is not chemically reacting with anything. So it is bombarding and dropping, and pure silver is dropping on the glass, forming a silver layer. Actually, it's quite a lot, which can be told about the process. But for example, if you need to deposit like silicium nitride, then you put a silica target on top and you put the nitrogen gas. So in the process of moving to the glass, you get nitride of silica and there forming special layer again. Coating machine usually consists of many chambers. Sometimes it's more than 20. And this is used to turn them on and off to produce different type of coatings in a single coating campaign. And with the speed of glass, with the energy in there, you can regulate the thickness of the layer individually. So we can have, as a result of the magnetron process, we can have a multi-layered coating with different thickness and different materials of the glass. What it allows us to do. Here is the computer graphics, which shows how it looks like in reality. Actually, in reality, it looks even more beautiful with the different area, the different color of the plasma. But you can also always see that when will be visiting our factory or some other factories who are making soft-coated glass. So again, what is the result? Result is the coating with many layers. To give you an analog of this, let's imagine that uncoated float is the piece of bread. So just pure bread. With the hard coating, you are applying one layer of something. Here is butter. If you want to change the taste of your sandwich, if you have the same butter, you have to change the bread, so meaning the color of the glass, the underlay. But with the soft coated glass, in order to get a tasty sandwich, you won't do anything. You just change the layers in between the bread. So with the multiple layers in one coating, you can achieve different levels of light transmission. With that, you can get a color on the glass. So color is made by the coating and not the glass. In there, you can have a solar control properties. And in there, you can have you can make it low E with 1 or 2 layers of silver. So magnetron process allows you much more diversity and much more flexibility in making the coatings. That is why it is technically superior to the hard coated glass. Does it mean that hard coating is bad? Absolutely not. It has, both of them have some pluses and have some minuses. Sorry. So pyrolytic coating, single layer, and as a result of that, it has quite limited performance parameters. After that, after we're done talking about that, we will see the parameters yourself. What are the bonuses? Very durable chemically and physically. And that plays its role because in some cases, pyrolytic coating are the king of kings and cannot be replaced with magnetron. I will give you an example after that with bending, glass bending on the project. It has unlimited shelf life and very few issues during processing. So it doesn't require a lot from the processor, meaning it is easy to process, easy to make AGI units, and easy to ship it anywhere and store. Magnetron coatings, multiple layers. So performance-wise, magnetron coatings are almost always better than pyrolytic. But of course, there are pluses and the minuses. Minuses is there. Soft coatings have limited shelf life on the processor side and on the glass manufacturer side also. The coating durability is highly dependent on the layers which you're using, on the layer stack, it's called, which you're using. Some of them are quite durable, but if we're talking a coating with the low E properties, with the silver, they are all quite weak comparing to the pyrolytic ones. So, and the last but not least, the processor has to be able to work with them, meaning it requires special equipment. Let's go and see that step by step. But first, let us talk about how can we divide coatings by their functions. What functions can they perform in architectural sense? First one is, of course, solar protection or solar control. Solar control can be both hard and soft coated glass. There is not really much difference in the characteristics between them either. So quite simple, and basically the solar control coatings are where the magnetron process started. Then we have energy saving or low E glass. Here we can also have both hard and soft coatings, but in this field, soft coatings are way better. That is because in terms of energy performance, the emissivity determines the U value. And the emissivity of soft coated glass is way better or way lower than the hard coated counterparts. For example, one of the best hard coatings have an emissivity of something like 0.15 or along those lines. The best soft coated glass have an emissivity of 0.01. See, the difference is great. So in terms of energy saving and U value, soft coatings are almost always better. And of course, you can combine solar control and low E functions into one glass. That glass sometimes called multifunctional, glass with the coating. And true solar control plus low E can be obtained only on the soft coated glass, in which the performance is excellent. Again, that is because we have a lot to do with the different layers. If you want to divide soft coating types, the simplest of them is the low E or energy saving coatings. As we're talking about Pilkington products, it is OptiTherm and OptiTherm 3 Pro T. And there comes another thing. If the pyrolytic coatings then can be used annealed, they can be used tempered, and there is no different types of them. In many types of soft coatings, different coatings are used, whether they be intended for use annealed and for tempered, for heat or heat treated. Usually in Pilkington, the temperable versions are called Pro T. They have a Pro T index. And annealed version doesn't have any. So T means tempering. Our competitors, almost all of them, also have some kind of T letter involved in the name. So not much difference here. Annealed versions cannot be tempered because coating will die during the tempering process. On the contrary, temperable coatings have to be tempered in order for them to achieve characteristics. Because before tempering, their characteristics usually worse than after. That is made because soft coating has to survive tempering process. And the second one, because if it has, in order to survive, it has to have some recombination inside of this very thin layer. So the properties which are used for us in the booklets, in the brochures, they are attained after the coat, after the tempering process is done. So first, low E, just for U value. Then soft coatings for solar control. Pilkington doesn't produce any of that type of the soft coatings. We are using hard coated glass for just solar control properties. So I won't put any names here, sorry. And then our top products is either single silver or a double silver coatings. The more silver you have, the better the properties, the better the numbers. And with the double silver, you can get a truly selective glass for you. What is selective glass? I will tell you right after that. But for the single silver, we have a SunCool 1 product range, and double silver is our headliner, the top products. They're called SunCool or SunCool Pro T for the temperable versions. Again, if you have any questions, please feel free to post them into the chat section. Let's move on to characteristics. And here is the comparison, the properties comparison between different types of IG units. I've compared in light transmission and reflection characteristics, energy parameters, meaning solar factor, and U value for an IG unit here, except for the first one. Here is just a single sheet of coating. For the convenience, I took energy advantage glass, which is also Pilkington produced. So, as you may see, here are the hard coatings. There. And here are double silver soft coatings. And in between them, just for comparison, a single silver coating. Let us see. For example, if we are using an IG unit with the pyrolytic glass, solar control pyrolytic glass, which might you having some low E also, let us compare them with the double silver. As you may see, I've chosen the products with a comparable light transmission. Light reflection of them, almost the same. But when we arrive to the energy parameters, let us see the solar factor. At first, when you're using hard coated paired with an ordinary float, you have a certain parameters. Are they good? Not that much. But when you put a low E glass in there, you do not only have a decrease of a U value, so U value is way better, but you also see that the solar factor also goes down there. Now, why that is happening, I will be explaining right after this slide. Now, just see the dynamics. And of course, if we compare those with the double silver products, you immediately see the difference between those. So with just one coating paired with float glass, you can achieve solar factor, which is in fact much lower than for the hard coatings. Why is that happening? Let us see on the next slides. In order to understand how does it happen, we have to see the graph. I will be already showing this graph before, but I will repeat a little bit again. At first, we have an energy with which sun is shining on us. Out of this energy, we have a visible spectrum, this one. This is a visible light, which we can see, and light transmission belongs to this part of the spectrum. But after that, we have infrared, shortwave infrared spectrum, which is exactly how it's called. This is the solar heat, which we do not see, but which contributes quite heavily into heating our building up. And now let's watch how does the glass behaves. Float glass have a high transmittance in visible spectrum, but also it doesn't stop solar heat from coming in. If we apply just pyrolytic coating, we may get less visible light, but also less heat in there. Does it give us solar protection? Yes, but it also lowers the amount of natural daylight which is passing through. What can we achieve with the selective glass, double silver? The graph becomes like that, see red one. So with using of silver, several layers of silver, we can get the effect that solar light is coming through almost unabated, and solar heat is mostly stopped on its tracks. Let us watch a little bit more how this performs. Let's say we have an IG unit with the hard coating as an outer glass and normal float as an inner one. So some portion of solar energy coming directly through the glass, it's direct transmission. But some portion of the solar heat is absorbed by the outer glass and then re-emitted in both ways. So the sum of these two energy is the solar factor. So solar factor is how much heat is getting through the IG unit inside the building in percent. What do we get here? The darker the outer glass, the more it absorbs. So the more of the solar heat stops being solar heat, but instead, after absorbing and re-emitting, the re-emitted heat is on the completely different wavelength. It's not solar heat anymore. It's like what we call normal heat. That heat emitted by the low temperature things like us, batteries, heating devices. So it is far infrared radiation, different wavelength. So, okay. What can we do? We can install a low E coating as an inner pane to increase the solar factor. Now, why does the solar factor increases here? Because again, the re-emitted radiation, this one, is the long wave infrared heat, so our heat. And low E glass is designed exactly to counter that type of heat. Low E doesn't design for countering solar energy. It designs to counter normal low temperature heat. So what it does, if you got coating right here, it reflects it back. So the amount of this type of heat which is coming through is much reduced if you put low E glass there. And that is why low E, when combined with the pyrolytic coating or body tinted glass, it helps a lot with the solar factor. And why the solar factor for a single sheet solar control glass is usually quite high. See, you get almost 10% decrease in solar factor just by putting low E into that. So what are we doing? Because performance-wise, hard coatings are lacking, we're putting some kind of support by using a soft coated glass to support the hard coating in Uvalue and in solar control. Because again, hard coatings are quite limited in performance because only one layer. But what happens if we have a soft coating, for example, a double silver one? At first, direct transmission of the solar heat is much lower because of silver. But what about the absorbed heat? Again, on the soft coating with low E performance, this side is low E. What does it mean? That the heat which is absorbed is not emitted inside the building almost at all. And the combination of lowering the direct heat transmission and the low E properties of the coating, that two things give us a very good solar factor, meaning very low one. In the meanwhile, usually soft coating does not obstruct any light transmission in there. So we get a lot of light, but very low amount of heat. And that is the purpose of putting several layers of silver into the coating. That is why it is done. With an excellent solar protection in mind, exactly. Now I hope everyone understands anything because I don't get any questions. That means one of two things. Either everything is understood and the second one is nothing is understood. I hope it's the first one. So let us move on. And that flexibility of the soft coatings and the layer combinations gives our product range a wide variety of characteristics. For sun-cool, the range of light transmission is from very high to very low. You can get colored versions of the glass if you want some color. For normal neutral colors, the light reflection is usually from very low to medium. If you want a very high reflective glass, yes, the colored versions are ready to provide that in case you want different. But what is the combination? It is all combined with the very low solar factor and a very good U value for all of the glass, soft coated glass that we produce. That means for a double IG unit, standard one, you don't need to put any extra coated glass in order to achieve best U value. Just put in some argon to increase the characteristics and you're good. These characteristics are always argon. So in here, in this table, you see the whole product range of our plant. And basically choose the one which you like. But what about the U value, which is also important? In cold countries like Russia, U value is extremely important because we have to heat up in the winter. But for the hot countries, which are located near the equator, U value is also important in order to prevent the normal heat, so not from the sun, but the hot air coming through inside. And here we can take a look at the characteristics for the U value. As you can see, hard coatings are working good only when combined with low E. And the best performance can be achieved if you put in some argon, which also adds a lot to the U value. So these are calculated for standard European temperature range, standard U value calculation range. See, for the hot climates, we are almost always using smaller spacers, but the smaller spacers gives you which is worse than usual one. And when you look here, these values are given for the 16mm spacer filled with argon. When we're decreasing the spacer width, some of this U value goes away, unfortunately. If you want to know in depth how the U value works, please see my previous webinars. And again, for those who are late, I will be posting a link to the YouTube channel. So you can find the previous webinars being published right there. But let us move on. And these are a composition, the U values for a cold climate. So as you can see, for a cold climate, it's very frequent, for example, in our country, in Mongolia, in Europe, to use triple IG units. Because for during the cold period, you really want to conserve this energy and spend much less on heating the building up. So the U value here is quite different. Why I'm emphasizing on U value even for the hot climates? That is simply because, as far as I've encountered, a lot of people underestimate the importance of U value in terms of stopping the heat from the hot air from coming into the building. And if you do a calculation of building energy performance based on these results, then you will understand that with the good U value, you may reduce your air conditioning by up to 25%, and that gives you a huge saving if, for example, you are building an office building, which is air conditioning 24/7 all the time. In terms of this calculation performance, we are doing it, and in the future we will be having a webinar explaining you about how do we do it and how you can save on energy and save on the cost of air conditioning equipment to begin with. Because if you have low heat gain, then you may use cheaper versions or less powerful versions of air conditioning systems in your building, which would be enough. And that helps you save a lot during a building period. But that's all for characteristics. Now let's see how it does looks like in terms of glass processing. Let's go step by step. And we start from the glass storage and the cutting. Hard coatings, unlimited storage time, unlimited shelf life. For example, hard-coated pack can stay in your warehouse for 2 years or more, undisturbed, and nothing will be done with this coating. But in terms of warehouse logistics, it's not really a good thing when something stays there for 2 years or more, because that means it takes your available storage space. Soft-coated glass, limited shelf time. Half a year, 1 year, depending on the coating type and depending on the conditions on the warehouse, mostly humidity and temperature. Also, in terms of glass cutting, hard coatings doesn't require edge deletion. Soft coatings, most of them do. That slows up a little bit the cutting process, but from my experience, the cutting is not the bottleneck of your production or your manufacturing logistics. You can encounter problems only when you are dealing with some kind of step glazing with the very wide step area. So yes, then the process is slowing considerably if we're talking about soft coatings, because you have to take out a lot of coating. That makes your cutting tables quite occupied. Let's move on to the tempering. And there we encounter the first real obstacle, because your tempering furnace has to have convection in order to temper properly a soft-coated glass. Soft-coated glass, again, usually has low E properties, and without the top convection furnace, you will not be able to temper it properly. So it will have visual defects for sure. At least some kind of top conversion is a necessary requirement. But in my experience, most of the modern glass processing companies already has a convection furnace, whether they be top convection or full convection ones. As long as you have a proper furnace, and no, that's not an advertisement of Glasstone in any way, there are plenty of other types. As long as you have a proper furnace, you shouldn't be having any problems tempering soft-coated glass. A special care should be taken when washing and handling the soft-coated glass. Special washing machines, special gloves, special care and training of your employees is absolutely required. But again, most of the processing companies already know it and already know how to work with the soft-coated glass. Now, yeah, what I forgot to mention, it's in the tempering section. The thing is that the hard coating is shining when you are talking about bending. When you have I will use that as a reference. When you have a standard bending, your coating and to be positioned on this side, on the inner side of bent glass. Why is that? That is because coating cannot, soft coated glass, the coating cannot be put on the rollers of the furnace. So if you have facade which looks like this from the inside, so bent outwards of the building, don't have any problems. Soft coating is positioned on the surface too, everything's fine. But when the facade is bent inwards, it's time for the hard coating, because that means the coating has to be positioned on the bottom of the glass, and soft coating does not survive the tempering process and bending in this regard. Same applies if you have double bent facade. So some parts of it are bending outwards, while the other are bending inwards. And I am afraid in this case, you have to use hard coated glass, which, mind you, Pilkington has a plenty. Just not produced on our factory. So again, niche purposes, hard coated glass is very good. Also, hard coated glass is extensively used for electrically heated IG units, for canopies, glass floors, heated glass floors. Perfectly fine with the hard coating. Now let's talk about a little bit about ceramic painting or ceramic print. Soft coated glass can be printed, can be painted, but here you will again may have several problems on the tempering side. Simply because if you paint half a glass with the paint and leave half of the glass with the coating on it, that means the coating, half of the glass is having low E properties, while the other does not. And it's sometimes really dangerous to put such kind of detail into the tempering furnace, because these two parts of the glass will be heated very differently, and the glass may break in the heating chamber. For a processor, this is quite a disaster, because in this case, tempering furnace has to be stopped for several days and cleaned up. And also the rollers, ceramic rollers, which are quite expensive, they also can be damaged. That's the first thing. The second thing, which you need to remember, if you apply a paint directly on the coating may go a little bit, change a little bit, color a little bit, go goldish, for example, as you can see on the photo. Sorry, this is like some kind of production place, so a lot of boxes there. So as you can see, in the central part, the reflection is quite whitish, while on the edge zones, the color goes goldish. Mind you, it doesn't look bad, and the architect may even like the look of it, but yet again, you need to take care of that, and you need to make samples in advance. Other than that, why not? If you want to apply some kind of dots, sure, go ahead. And the edge unit assembly, that's your last stage. And if the coating survives it to there, you shouldn't be having any problems there, apart from, again, washing machine and handling. So don't leave a fingerprints on it. So to sum it up, hard coatings have niche applications, unlimited shelf life yet again, very durable, doesn't require a lot from the processor, but very inferior in terms of characteristics. Soft coatings, superior characteristics, sometimes much superior to the hard coated ones. You don't have to use a low E as an opposite on an opposite glass, but they require skill and expertise from the producer, from the processor. After the processor is done making IG units, job's done, coating is ready to perform and nothing threatens it when it is inside of an IG unit.